A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Every single JSON object you send to an API eventually has to settle down somewhere. And usually, that home is a row in a SQL database. But the translation between those two worlds, JSON schema and SQL types, is absolutely littered with subtle traps. It looksification simple on the surface, but if you stop at the surface, you end up with performance degradation, data integrity nightmares, and columns that just don't make sense 6 months later.
It is a classic impedance mismatch problem, Corn. People think because they can just dump a JSON blob into a database now, the schema design doesn't matter. But the reality is that the mapping between a JSON string and a SQL varchar, or a JSON number and a SQL numeric, carries massive implications for how your application scales. By the way, listeners, today's episode is powered by Google Gemini 1.5 Flash, which is helping us navigate these technical weeds.
I'm glad we have the help, because today's prompt from Daniel is really pushing us into the engine room of back-end architecture. He wants us to look at the foundational mappings, the weird specialized SQL types people forget exist, and the strategic use of JSON-L as a storage format. It's basically a therapy session for anyone who has ever had to run a migration on a table with 10 million rows because they picked the wrong integer size.
Herman Poppleberry here, ready to defend the honor of the Postgres type system. Honestly, Daniel is hitting on something huge. We live in an API-first world where JSON is the lingua franca, but our systems of record are still predominantly relational. If you don't understand how a JSON number actually behaves when it hits a SQL float versus a decimal, you're going to have a bad time when someone tries to store a high-precision financial value.
Let's start with the basics then. JSON schema has these 6 primitives: string, number, integer, boolean, object, array, and null. On paper, they map one-to-one to SQL. String to varchar, check. Boolean to boolean, check. But as soon as you look closer, the number type in JSON is a total disaster for a database engineer, isn't it?
It's a nightmare. In JSON schema, number can be anything: an integer, a floating point number, a double. But SQL is pedantic. It demands to know, is this an exact numeric value like a decimal or numeric, or is it an approximate value like a float or real?
Wait, can you break that down? Why does approximate even exist in a world of precision computers?
It's all about the trade-off between space and speed. A float uses IEEE 754 floating point math. It's processed directly by the CPU's floating point unit, so it's incredibly fast for scientific calculations or graphics. But it's inherently imprecise because it represents numbers as powers of 2. If you just map every JSON number to a float in your database, you're introducing rounding errors that will haunt your calculations. Imagine a shopping cart where the total is a JSON number. If you store that as a float, eventually 2 plus 2 might equal 4.000001,
and then your accountant starts crying. I've seen this happen in real time with currency conversion. You convert $10 to euros and back, and suddenly you've lost a fraction of a cent because of a float. So, for anything financial, the rule is always num, aric, or decimal, right?
Always. Those are arbitrary precision types. The database stores them almost like a string of digits, so there is no rounding error unless you explicitly tell it to round. It's slower to calculate, but it's correct. When you're looking at a JSON schema, if you see a number type, you should immediately be asking, does this represent money, or does it represent the temperature of a sensor? If it's the latter, float is fine. If it's the former, you better be using numeric 19.4 or something similar.
But what happens if you have a massive dataset of sensor readings? If I have a billion rows of temperature data, is the performance hit of numeric actually noticeable, or is that just old school DBA paranoia?
Oh, it's very real. If you're doing aggregations, like calculating the average temperature across a million sensors, numeric is significantly slower because the CPU can't use its native floating point hardware. It has to do the math and software, essentially. So if you use numeric for everything just to be safe, you might end up with a dashboard that takes 10 seconds to load instead of 200 milliseconds. You have to pick your poison, absolute precision or raw speed.
Let's talk about the integer type. JSON Schema actually added integer as a distinct type from number, which helps. But even then, SQL makes you choose. Do you want a small int, an int, or a big int? In JavaScript land, where a lot of this JSON is consumed, every number is technically a 64-bit float under the hood anyway. So, if I send a huge ID as a JSON integer, and my SQL column is just a standard 32-bit int, the database is going to throw a fit the moment that ID crosses 2 billion.
That is exactly the Y2K of the modern era, the overflow of the 32-bit integer. I've seen production systems go down because a primary key was defined as a standard int and the business was just too successful. They hit row 2,147,483,647, and suddenly the database stops accepting new records.
That is a very specific number. You've been waiting to say that for a long time, haven't you?
It's burned into my retinas, corn. It's the maximum value of a signed 32-bit integer. If you're using JSON Schema to validate your inputs, you really should be specifying minimum and maximum values that match your SQL constraints. If your database uses a bigint, which is 64-bit, you're safe for several quintillion rows. But here's the kicker. JavaScript can't actually represent a 64-bit integer precisely above 9 quadrillion without using the t-biginty type. So even if your SQL is ready, your JSON parser might mangle the ID before it even gets to the database.
That's a terrifying thought. You send a long ID from the server. The browser parses it, rounds it to the nearest representable float, and then sends back the wrong ID when the user clicks save. You end up updating the wrong record.
This is why many APIs actually send 64-bit integers as strings in JSON, even though they are technically numbers. It's a safety measure. If you see an API where the user read is a string like 920.2337236854777807, that's why. They are protecting the integrity of the mapping.
It's sort of a don't trust the transport layer mentality. But if I'm using strings for IDs, doesn't that make the JSON schema look a bit messy? You have a field called tita, but the type is tita string instead of tintiger.
It does feel a bit hacky, but it's the industry standard for a reason. Twitter Snowflake IDs are a classic example. They are 64-bit integers, but their API documentation explicitly tells you to use the distr field because they know standard JSON parsers in browsers will truncate the numerical didit field. It's a defense in-depth strategy.
Let's look at strings. This is another area where the mapping feels obvious but isn't. In JSON, a string is just a string. It's unbounded. But in the SQL world, the legacy of Varchar 255 still looms large. Why was it always 255? Because in older versions of MySQL and other engines, that was the limit for storing the length in a single byte.
It's funny how these ancient constraints still dictate how people design APIs today. You see max length 255 in JSON schemas all over the place just because some DBA in 2004 said so. But modern databases, especially Postgres 15 and 16, have basically removed the performance penalty for using text or varchar without a limit.
Is there any reason to keep those arbitrary limits anymore, other than preventing some malicious actor from sending you a 4 GB string as a username?
That's the main reason, application level sanity. But strictly from a database storage perspective, in Postgres, varchar and text are stored identically. There is no speed advantage to limiting a string to 50 characters if the data is usually 10 characters. The real trap with strings is actually encoding and collation. JSON is UTF-8 by default. If your SQL database is still sitting on some legacy, Latin 1 encoding, you're going to get mojibeke, those weird garbled characters, the moment someone signs up with an emoji in their name.
I love the word mojibeke. It sounds like a delicious Japanese dessert that actually tastes like binary errors. But it's a real pain for search, right? If your collation is wrong, the database might not think A and A are different, or it might sort them in a way that makes no sense to the user.
Precisely. And if you're mapping a JSON string to a SQL column, you also have to think about trailing spaces. Some older SQL types like Sharon will pad your string with spaces to fill the length. So corn becomes corn followed by 251 spaces. When that goes back to the JSON API, your front end might not be expecting that padding, and suddenly your UI looks broken.
Wait, does CHARN actually save space? I've heard people argue that for fixed-length things like ISO country codes, CHAR2 is better than varchar2.
In most modern engines, the difference is negligible. In fact, in Postgres, cchar usually takes more space because of that padding. It's almost always better to just use varchar or text. The only time chrn really makes sense is in very specific legacy systems, or if you're using an engine where the row size needs to be perfectly predictable for disk offsets. But for 99% of web APIs, avoid it like the plague.
What about booleans? That should be the easiest one, right? True or false?
You'd think so. But SQL history is messy. PostgreSQL has a native Boolean type that works great, but MySQL for the longest time didn't have a true Boolean. It used tinyInt1 where 0 is false and 1 is true. If your application code is expecting a literal JSON true, but the database returns the number 1, your front end might break if it's using strict equality checks, the triple equals in JavaScript.
I've been bitten by that. You write if user dot is active true, and it fails because the database sent back ATD. It's these little mapping layers, the ORMs or the database drivers, that have to do the heavy lifting to make sure a JSON true stays a true, all the way down to the disk and back.
And don't forget the tri-state Boolean. JSON allows true as, false, and null. SQL allows ACWL, ACRUS, false, and null. But if your JSON schema says the field is required but nullable, you have to be very careful that your SQL column doesn't have a not null constraint with a default of false. If it does, you've just lost the null state forever.
It's like a game of telephone where the database is a grumpy old man who only speaks in bits, and the API is a trendy teenager who only speaks in objects. Let's move into the more exotic stuff Daniel mentioned. SQL has types that JSON doesn't even dream of. I'm talking about things like UUIDs, CIDR blocks for networking, and range types.
This is where SQL really flexes. Take UUIDs. In JSON, a UUID is just a string. To a JSON validator, 55T8400E29B414D4A7162466544000 is just 36 characters, but a native UUID type in SQL is stored as a 16-byte binary value. It's way more efficient to index, way faster to compare, and the database can actually validate that it's a well-formed UUID.
And we've seen a shift recently with UUID versions, right? Everyone used to use UUID v4, which is totally random, but now everyone is talking about UUID v7. Why is that such a big deal for the database?
It's all about the B-tree index. UUID v4 is random, which means when you insert a new row, the index entry could go anywhere. This causes index fragmentation. Imagine a library where new books are placed on shelves at total random. Every time you add a book, you might have to shift 10 other books to make room. That's what happens to your database pages with random UUIDs.
So UUID v7 is like putting the books on the shelf in the order they arrived.
UUID v7 is time-ordered. It has a 48-bit timestamp baked into the first several bytes. So, new UUIDs are always greater than old ones. This means they get appended to the end of the index, which is massive for performance on high-write systems. It gives you the uniqueness of a UUID with the insert performance of a sequential integer. If you're building a system that expects millions of inserts, you should be mapping your JSON IDID string to a UUID v7 column in SQL.
How does the JSON schema handle that though? Is there a specific format tag for UUID v7, or do we just use the generic UUID format?
Most validators just use the generic UUID format, which checks the structure but doesn't necessarily care about the version. You usually handle the versioning at the application level, when you generate the ID, or at the database level using a default function. But by documenting it in your schema as format, UUID, you're at least signaling to the consumer that this isn't just any old string.
That's a huge win. It's basically having your cake and eating it too, as long as the cake is a 16-byte hex string. What about network types? I feel like most people just store IP addresses as strings and call it a day. Why bother with the INET type in Postgres?
Because it lets the database do the work for you. If you store an IP as an INET, you can write queries like find all rows where the IP is within this subnet. If it's just a string, you're stuck doing messy string manipulation or regex, which is slow and error prone. The INET type handles both IPv4 and IPv6 seamlessly. It's a classic example of don't reinvent the wheel in your application code if the database can do it in microseconds.
I remember seeing an interval type too. That one always confused me. Instead of storing a duration as an integer of seconds, you store it as an interval.
Intervals are brilliant for human-readable logic. You can store 3 hours, 20 minutes directly. Then you can do math, select, now plus interval column. If you store it as seconds, you're constantly doing math in your head or your code to convert it back to something a human understands. Plus, intervals handle things like daylight savings transitions much more gracefully than raw seconds do. If you add 24 hours to a timestamp, you might end up at the wrong time of day if a DST jump happened. If you add 1 day as an interval, the database knows how to handle the jump.
But wait, how do you send an interval over a JSON API? There isn't a standard JSON duration type. Do you use ISO 8601 strings or just stick to seconds and convert it on the way in?
ISO 8601 is the way to go. A string like P3DT4H for 3 days and 4 hours. It's a bit of a pain to parse in some languages, but it preserves the semantic meaning. If you just send 2736 true seconds, the database doesn't know if you meant exactly 76 hours or if you meant 3 days and 4 hours in a context where days might have variable lengths.
Okay, let's talk about the elephant in the room. JSON-B in Postgres. This is the ultimate I don't want to choose a type. Daniel brought up a great point about when to use a rigid schema versus just dumping everything into a JSON-B column. We actually touched on this a bit in that older episode. Is your JSON store just a Postgres feature now? But it's worth revisiting because the Just Use Postgres movement has only gotten stronger since then.
It really has. JSON-B is binary JSON. It's not just a text blob, it's a decomposed binary format that the database can actually query. You can create a GIN index, a generalized inverted index on a JSON-B column, and suddenly you can search for any key value pair inside that blob with incredible speed. It effectively turns Postgres into a document database like MongoDB, but with all the ACIZ guarantees of a relational system.
So if I can index it and it's fast, why would I ever define a regular column again? Why not just have a table with 2 columns, id and data, where data is just one giant JSON-B blob?
Because there's always a catch, Corn. JSON-B has overhead. It's larger on disk than a specialized column because it has to store the keys over and over again for every row. If you have a million rows and every row has a key called user first name, you are storing that string a million times. In a traditional column, the name of the column is stored once in the table metadata.
That seems like a lot of wasted space. Is there a performance hit on updates too?
A huge one. If you want to update one small value inside a 100 KB JSON-B blob, the database often has to rewrite the entire blob. If that value was in its own column, the database only has to update those few bytes. Also, you lose type safety at the database level. JSON-B doesn't care if age is a string in one row and an integer in another. That leads to data rot, where your application code starts crashing because it encounters a format it didn't expect.
Right, so the hybrid approach is the way to go. You normalize the stuff you know, the identity, the timestamps, the status codes, and then you have a metadata or extra attributes JSON-B column for the weird variable stuff. It's like having a clean, organized closet, but also a junk drawer for the things that don't have a clear home.
And Postgres actually has a cool feature called generated columns that bridges this gap. You can have a JSON-B blob, but then you can have a real SQL column that automatically extracts a specific value from that JSON-B and indexes it. It's the best of both worlds. You keep the flexibility of the blob, but you get the performance and structure of a typed column for the fields you care about most.
So, if I have a settings JSONB column, and I realize everyone is suddenly querying for the theme setting, I can just add a generated column for theme without having to migrate the whole table or change my API.
Precisely. You add the generated column, Postgres populates it by parsing the JSON B in the background, and then you can put a standard B-tree index on that new column. It's an incredibly powerful way to evolve your schema as your application's access patterns change.
That brings us to Daniel's last point, JSON-L, or JSON lines. This is a format where every line in a file is a separate JSON object. It's huge in the world of logging and data engineering, but people are starting to use it as a storage strategy inside the database too.
Wait, why would I use JSON-IL instead of a JSON array? If I have a list of events for a user, why not just store them as a JSON-B array? Scaling. If you have a JSON array with 10,000 elements and you want to add one more, the database usually has to read the whole array, append the item, and write the whole thing back to disk. That's an ON operation that gets slower and slower as the list grows. JSON-L is append only by nature. In a file system, you just slap a new line at the end. In a database context, people often use a text column and just append new JSON objects separated by new lines. It's a very lightweight way to do event sourcing or audit logs where you don't need to query the individual lines often, but you need to write them very fast.
But how do you actually query that? You can't exactly run a where clause on the third line of a text blob very easily.
You don't. That's the trade-off. JSON-L in a database is for cold storage, or write-heavy audit trails. If you need to query it, you usually hydrate it into a proper table later through some background process. Think of it as a waiting room for data. It's great for high-volume ingestion where you don't want the database to spend time validating schemas or updating complex indexes while the user is waiting for a response.
So let's say I'm building a logging system for a high-traffic site. I'd stream the JSON objects as lines into a single column, and then every hour a worker process reads those lines and inserts them into a structured table.
Precisely. It prevents your primary transactions table from being bogged down by the sheer volume of log data. It's a pattern called log structured storage, and while databases like Cassandra use it internally, you can mimic it in SQL using JSON-L for specific use cases. It's incredibly resilient. If your schema changes, the JSON-L doesn't care. You can fix the hydration logic later without losing any data.
Is there a risk of the file getting too big to read? If I have a log data column that's 50 MB of JSON-L text, won't the worker process choke on it?
That's where you have to be smart about chunking. You don't store the whole history in one row. You might have a log batch table where each row contains maybe 1,000 lines of JSON-L. Once a row hits that limit, you start a new row. It keeps things manageable and allows you to process the batches in parallel.
This whole conversation makes me realize how much magic we expect from our tools. We want the flexibility of JSON because it's easy to code with, but we want the rigor of SQL because we don't want our data to turn into a swamp.
It's the eternal struggle of the back-end engineer. We're basically translators. We're translating human intent into code, code into JSON, and JSON into bits on a platter. If you lose the meaning at any of those steps, like by picking a float when you meant a decimal, the whole thing eventually falls apart.
Let's talk about a real-world case study for a second. Think about an e-commerce platform. They start out with a simple JSON schema for product. They have a name, a price, and a description. They map these to varchar, dexmol, and text. Simple, right?
Until they start adding attributes. One product is a shirt with a size and color. Another is a laptop with RAM and CPU.
If they try to create a SQL column for every possible attribute, they'll have a table with 500 columns, 490 of which are NULL for any given row. That's a nightmare to manage.
That's the perfect use case for the hybrid JSON-B approach we discussed. The core identity, the SKU, the base price, the stock level, stays in rigid SQL columns. The specs go into a JSON-B blob. But here's the Daniel level tip. You should still use a JSON schema to validate that JSON-B blob before it gets saved. Just because the database allows anything doesn't mean your application should.
So you're saying even if the storage is flexible, the entry point should be rigid?
Always. If you don't validate the JSON against a schema before it hits the JSON-B column, you're just deferring the pain. Eventually, some developer will typo color as color, and half your products won't show up in the search results because the index is looking for the wrong key.
I've actually seen companies build dynamic schema engines where the JSON schema itself is stored in the database, and every time a JSON-B column is updated, a trigger runs to validate the data against that stored schema. Is that overkill?
It's powerful, but it can be a performance killer. Triggers add latency to every write. I usually prefer doing that validation in the application layer or using a middleware. But if you absolutely must ensure data integrity at the database level, Postgres does have extensions that allow for JSON schema validation directly in a check constraint. It's hardcore, but it works.
Well, before we fall apart, let's look at some practical takeaways. If someone is sitting down today to design a new API and a new database schema, what's the golden rule for mapping these types?
Rule number 1. Use the most specific SQL type possible. If it's a date, use date. If it's a timestamp, use timestamp CZ, always with the time zone. If it's a fixed precision number, use numeric. Don't fall into the trap of everything is a string or everything is a number.
And rule number 2. Validate at the boundary. Don't let your database be the first thing that realizes a number is actually a string. Use your JSON schema to enforce those constraints before the data even touches your backend logic. It saves you from those ugly database constraint violation errors that are hard to surface to the user.
And rule number 3, embrace the hybrid. Don't be afraid of JSON-B, but don't let it become a crutch. If you find yourself querying a specific key inside a JSON-B column more than 10% of the time, it's time to promote that key to its own dedicated column. Your CPU and your future self will thank you.
I like that. Promotion for keys. It's like a corporate ladder for data. If you work hard enough in the JSON-B junk drawer, you might eventually get your own column in the main table.
Just don't let the power go to your head, or you'll end up as a primary key with way too many indexes.
One last thing before we wrap up. What about the null versus undefined distinction in JSON? SQL doesn't really have undefined, it just has NULL. How do you handle that mapping?
That is the bane of my existence. In JSON, a missing key is different from a key set to null. In SQL, they both usually end up as NULL. If the distinction matters to your business logic, like the user didn't provide a phone number versus the user explicitly cleared their phone number, you actually have to store that metadata separately or use a sentinel value. It's one of those areas where the translation isn't perfect and you have to be very intentional about how you handle it.
Could you use a JSON-B column just for those optional states? Like, if the key exists in JSON-B, it was provided. If not, it's undefined.
You absolutely can. That's one of the few places where JSON-B's ability to distinguish between a missing key and a null value actually shines. If you need that level of granularity, JSON-B is your best friend. But again, you pay for it in complexity when it comes time to write your SQL queries.
This has been a great dive into the plumbing. It's the kind of stuff that isn't sexy until your database is on fire at 3 in the morning because of a type mismatch or a 32-bit integer overflow. Thanks for the prompt, Daniel. It's always good to get back to the foundations and remind ourselves that the boring stuff is actually what keeps the world running.
Definitely. It's easy to get lost in the high-level vibes of AI and automation, but at the end of the day, it all comes down to how we store those ones and zeros. If the foundation is shaky, the AI on top of it is just going to hallucinate based on bad data. And honestly, the more complex our systems get, the more we need to rely on the pedantic nature of SQL to keep us honest.
Big thanks to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes. And a huge shout out to Modal for providing the GPU credits that power this show. We couldn't do this without that serverless horsepower.
If you found this useful, or if you've ever had a number, precision error ruin your weekend, leave us a review on Apple Podcasts or Spotify. It actually helps other people find the show. We love hearing about your database horror stories, so keep them coming.
This has been my weird prompts. We'll catch you in the next one, hopefully with fewer rounding errors and more perfectly mapped UUIDs.
See ya. Keep your schemas tight and your indexes warm.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, my weird prompts, where our thoughts go from slow curious, keep weirding.